Okay, so let's do one more video on this topic that will show us some additional ways to extend SARSA and Q-learning to make them a bit more robust to certain types of problems they can get into. And these ideas will actually apply to some of the stuff when we're using deep learning to implement these algorithms, because here so far we've talked about a completely tabular way of implementing these algorithms, right? So our value function that we're using is really just a table that is still a table that tells us what's going to happen at every one of the states we encounter, right? And we're storing some number here. Right, so in both of these cases we have a table like this, an action, a state action value function, but we update it in different ways, right? And so the essential difference is that SARSA is your example of an on-policy method, where as you're exploring and gaining some reward and seeing what happens, you update your estimate for that state and action that you took, but you also, as part of that update, you need to find out what S prime, the next state, would be, right? So you took some action, you took some in some state, and you got some reward because of that. But you had to come up with an S prime, a next state, and you also had to come up with a next action that you would follow in order to figure out what the value of that next state would be. Right, and so they both do this so that they can update their value function, the Bellman equation, properly. And SARSA commits itself to saying, okay, I said I was going to take that action, that's the one I looked up in my table, I'm actually going to do that. Whereas in Q-learning, you don't. You say, I can do something else. When I get to that S prime state, then I can decide what I'm going to do again, and I'll actually pick some other action. Who knows? So SARSA, in a sense, is a bit more, conservative. It's going to stick to the thing it did. It's going to take the saved action that it actually evaluated. Because Q-learning is always going to look for the best thing to do. It's still epsilon greedy, so at every stage it could choose an action that is suboptimal, but it's basically not committing to the action that it used for its initial calculation. So that's the difference between on policy and off policy, which is an important concept, right? So here, this action A that was sampled is going to be used, and so when you come around to the next time, you're literally using SA and A prime again in the same one. Whereas in Q-learning, you take an action, but you basically find out what's the best one you could possibly take at that moment. Right, so you're maximizing your best action in the future. So you're assuming kind of in the future after this, you're not even following an epsilon greedy policy in your future steps, right? But then there's no A here, right? So when you come back in the next version of the loop, you only bring the S prime up. You choose an action again. It's a completely new action, so it does not necessarily have to match, right? Not necessarily, anyways. They could accidentally be the same, but they don't have to be, right? So this is we talked about some kind of different advantages, trade-offs between those two. And we're kind of in, as we were saying, we're kind of in this area of looking at ways to find the temporal difference, right? So the difference between our expected kind of value going forward well, here, the reward is real. So we got our reward we're getting and then expected reward we would get, and subtracting that from what we thought for that next step, and comparing that to, you know, what we initially thought we would have had when we got here, right? That's the essence of the temporal differences, because this QSA is really the original one that we're updating now. So before you took this action, what do you think you were going to get? And we're kind of deducting the difference, right? So if we are doing better, then this is going to be an increase. If we're doing worse than we expected, then we're going to have something negative, and this value is going to go down. But it still has, there's some problems these can get into. So they are both kind of sensitive to a kind of sample bias. So they learn from particular experiences, and they can get over-focused on those experiences and go off track. So there's two different ways to kind of deal with those for these algorithms. For SARSA, we have this algorithm called expected SARSA. And you could probably guess what it is based on the name we're using. But so in Q-learning, right, in Q-learning, we have a max here, right? So this is our formula for SARSA, right? So this is normal SARSA. Is it? No. No, this is all expected SARSA. So we had our normal SARSA one before, and if we thought about what the difference is, we had our QSA, right? And we have our learning rate alpha, and then we've got the return that we're actually receiving at this step, and we have a discount factor, and then we just use the values for that next state in action subtracted from our original expectation for it before we started. So now instead of saying, note the only reason I'll put this here is that it's just one thing, right? It's a single action that we're using. And in Q-learning, it's the same thing, right? We say max A, so we pick a particular one. It's only one. So one thing you could do is you could say, let's not just, why limit yourself to just one of these actions? Why not do all of them, right? So we're going to take an expectation over all of the actions that we could take. Right, so we're taking an expectation over actions, right? Because we know all of our actions that we could take, and we know, since we're doing temporal difference learning, we're using the future value for S prime and A prime, right? We're not actually getting a new reward here. That's the whole point of temporal differences, is that in these two parts of the formula here, we're using our existing values from our table, right? So we can just calculate as many hypothetical situations as we want, right? We're doing a single hypothetical situation here where we say, I pick some next action sampled from my policy, but in SARSA, that A is sampled from your epsilon greedy, right? Policy, and your policy is pi, right? So now instead of doing that, we'll say, well, let's do all the actions, right? Let's take an expectation over that, and let's do that by saying, I know my policy, and this gives me a probability, right? And so I have a probability for every one of those actions. I have the actual value that I'd look up in my table if I had it, and then I just go through all the actions. If there's 5 actions in this domain, the robot can go north, east, south, west, or stay put. that's 5, and you got a probability for each of those, and you do it. And that's the definition of an expectation, right? You're summing over a bunch of values weighted by the probability of occurring. And that's it, basically. So you're kind of taking a bit of this idea of, right, in Q-learning, you're saying max A, right, QSA. And now here you're going to be able to say the expected well, no, it's not over, I guess it's over A. So in a sense, you're taking a bit of the idea of Q-learning and going in Q-learning, you go through all of them, you pick the best one. In expected SARSA, you go over all of them and you weight them in proportion to how likely they are. Right? That's kind of halfway, in a sense, between SARSA and Q-learning. Assuming now you know, this does require you to know pi, your policy, right? So assuming you have some policy that says you have a 90% chance of taking some action for whatever the best action was. And the rest of the policy for all the other actions was this. Right, so in epsilon greedy policy, by definition, you could define it this way, right? You could say that this function that says, look at all the actions we have. You've got 4 actions to choose from. They have some values, right? And it picks the best one, and so the policy here gives you a 90% chance of choosing that one. And then the rest, 3 3/10 of chance of choosing all the others, right? Right, so I'm going to 0.333 for the other ones. And that will be your policy, right? In this case, so you know those probabilities, you have it here. So whatever your policy, your policy is, you could include those probabilities here, and that's how you would weight them. So once you're using that, otherwise the algorithm is exactly the same, and they have some results where they're computing it. So note there's the alpha, so we get the learning rate ranging from a very weak learning rate to like deterministic, where you overwrite everything every time, which is kind of bad, and a very low learning rate where it just takes you forever. You're very cautious about updating your value function. So given if you run it for 100 episodes with that learning rate, here's kind of what you're getting for different learning rates. So SARSA kind of is doing better over this short term than Q-learning, but in the asymptotic way, so if you run asymptotically, right, we say just run it until convergence, right, run it until it stops changing at all or very little, so run it a very long time. Q-learning is usually going to come out something better than SARSA, because SARSA might kind of get off track and get not as good a result. And SARSA is also, as you'll see with these ones, right, it's pretty sensitive to very high learning rates. So since it's on policy, SARSA doesn't do as much exploration, right? It only updates its values about things that it's actually seen. And so if it sticks to things it's seen, and then it updates its value, and you're always only basically replacing the value with old ones, it basically means it can get stuck if it's too certain about things. Whereas Q-learning is going off policy. Sometimes you're updating parts of the model that you don't actually go down. You say, well, let's assume we'll go that way because that's the best action. But then when you get to that state, you don't take that action. We had this example with the cliff walking in the previous lectures, right? That SARSA does well for cliff walking because it's more cautious, and it says, I'm only going to do things I'm sure work well with I've seen before, and it wouldn't try something. It won't update its values about places it's never been, whereas Q-learning would. So in a lot of cases, Q-learning will work faster because of that, but if you're talking about a very particular thing where one step to the left means you die because you fall off a cliff, SARSA would be safer, but you pay for that. So once you do this expected SARSA thing now, it's getting some of the advantage of Q-learning because it's getting to combine together all the actions that it didn't take, at least probabilistically, to see at their value, and you can see it kind of usually passes Q-learning in this case, and its expected convergence thing is much better, and it's no longer sensitive to this learning overlap because of it's averaging across the different actions based on their probability. So this problem of maximization bias is another one of these problems that Q-learning and some TD methods can fall into. So to understand this problem, consider this MDP here, where we start in state A, and we have two actions initially. We can go left or right. Right is the right action, left is the wrong action, and for those actions we get nothing. When we get to no reward, when we get to this one on the right, we stop, right? And on the left, instead of that, we then get a second choice, second action, and this action might have many actions possible. When you get to B, you can take many different actions, and the reward you get is going to be depending on a Gaussian distribution like this, with a wide variance and a mean of minus 0.1. And then you get the terminal action, you stop. Terminal state, and you stop. So you should be able to look and see what's the expected return for being in state B, right? If you're in B and you take some action, no matter what policy you follow, or if you follow it randomly, it should come out to negative 0.1, right? Because the mean of this is definitely negative 0.1. So eventually that's going to be what you converge to. That would at least be the expected value. But initially you might not find that, right? Initially you might get some quite high rewards that are above 0. And so when you do your max, because you're doing Q-learning, you're doing max Q, the maximum thing there might say, oh, well, this way's better because one time I went through there and I got, 0.5. Another time I went through and I got 0.7, or even just 0.1. Anything's better than 0. Because I go this way, I definitely get 0, right? So you could see how with a small number of samples, it could go this way, right? And so what we end up seeing with the Q-learning on a problem like this, where you could get some good rewards, but in the long run you're going to probably get something negative, is that it explores that way a lot. So it's trying out the wrong actions a lot, and then eventually figuring out that it gets down here. So what we want is something more like this, where it's not wasting its time off in this direction, and realizes more quickly that it is not better. So how can we do that? So a way we can get around this is using this double Q-learning approach, which kind of diversifies your function, the value function that you're learning, so that it's not combining together all of its experiences into one place. So it's a very simple idea. You basically have two Q functions, completely separate and independent. We're going to keep them independent all the time, And we're going to update both of them as we experience things, but we're going to randomly decide which one we're going to store our experience to. So it's like you have two brains and they both remember different parts of your life, but no overlaps at all. And they both learn stuff that are useful, but they'll disagree on things because they'll have different memories. They should both do fairly well, but the fact that they're both learning different experiences, so one time step might update from Q1, and the next couple will do Q2, and then the next one will do Q1. And then the essential part is that when you're updating Q1, so we randomly decide which one we're going to update. But while we update it, we use, our existing value for Q1 as our base, and then we're going to have our learning rate and our reward that we actually received from this step. And then for the future, right, our kind of idea about what we're going to do in S prime, A prime, right, we're going to use the other one, right? So you've got this kind of diversity of opinion. Like when you're deciding what to do next, you're going to remember, your brain one, you're going to remember what happened and codify this into memory based on the reward you got. But when you ask about, okay, what would happen next step, you don't use your own values, you use the other brain, right? And the other brain tells you what would happen next if you took the best possible action. And so they both get to have an opinion, but only one of them gets updated and essentially remembers this event. And this seems to help with this bias problem, right? Because you're kind of spreading it out across a couple of different functions. The implementation of it is quite simple because you're just doing that kind of randomization, right, where you just call it twice, and you have to call these functions. So you have to initialize the function twice and store them separately. But the idea then is that you're doing this in a more diverse way. And so when you use this approach, we don't get this problem where in the initial learning we're always taking the wrong action. We more quickly realize that one of the actions is a red herring and not kind of misleading, and more quickly converge to the optimal, whereas they kind of, in the default version of Q-learning, you go off track here for a long period and waste all this time learning because of the misleading nature of this. But this kind of structure could happen in other bigger networks where you don't even realize it's happening. Okay, so those are just two additional ideas that you have here about kind of implementing these algorithms, and we're going to try them out in the assignment. And we have these tree figures we've been using to kind of represent all the different approaches or ways of storing the value function, and all these different SARSA and Q-learning forms kind of can be explained by looking at these, right? Whether you're finding a max over a bunch of choices, choosing from a policy, or iterating over them exactly. So the summary kind of this, I guess, 2 weeks of topics are this whole family of methods that get us from the dynamic programming approach, where we're doing things exactly, to using randomization with Monte Carlo methods. We're saying we're going to do some sampling of our experiences and use that to update things, and then to do that in a more kind of efficient or computationally tractable way with TD methods, where we're finding the differences between values and only kind of updating with those, rather than having to go all the way through all possible states like we do in dynamic programming, or to the end of each episode like we do in Monte Carlo. We can do things incrementally as we go. And so these methods are going to work better as long as we don't have to remember, as we talked about at the very beginning last week, right? If the world is Markov, right? So if we don't have to remember things far in the past, then this is all going to work. And we kind of always still assuming that that's true, right? Yeah, and then we have a couple examples of algorithms doing that. And right, so in the next algorithms we'll get to, we'll do things in quite a different way, but then we'll cycle back to these and all the different families of them when we're looking at deep reinforcement learning. So we'll end up there.